Okay, so how are we all doing? Good. So today I thought I would start with a, I don't know, maybe a little bit of motivational advice. And this applies to some of you or to a lot of you. So how many of you are in the game stream? Okay. How many of you are interested in things like games, graphics, and so on? Okay. All right, so for those of you who put your hand up, great. For those of you who didn't, you can close your ears for now. So, who's heard of John Carmack? Yeah, so what's John Carmack famous for? Doom. And even earlier than that, Wolfenstein. So John Carmack has been making video games since the late 80s, early 90s. He's been a real pioneer in the field. So the first-person shooters with really good 3D graphics were done by him on incredibly, what by now is incredibly slow hardware. There were still very, very playable games, and ever since then he's been basically pushing the boundaries of what can be done in graphics. Right now, his company that he's involved with is Oculus Rift. Has anybody ever heard of that? Yeah. So that's this virtual reality headset world, and so he's a real hacker, real pioneer. Lots of good stuff has been said about him and his code. So much of the code from his earlier games has now been open sourced. And so people look at it and say, "Wow, this is really beautiful stuff." And you can find lots of interviews online with John Carmack and lots of question and answers. And one thing that he says frequently, and I just want to point out to you, and we'll see a bit of that today. So avoid cookbook programming. So that's where you're just cutting and pasting pieces of other people's code or maybe your own old code. Think about everything that you do and do it well. Work hard. Get lots of books that cover programming, not just what we do in class. Do the exercises. Work on them. Do great. And especially for you game developers, where are we? Pay attention to school and math classes. Okay, so you're all either taking or going to be taking algebra and calculus classes. You have all taken trigonometry in high school and maybe have forgotten it. It's really important to know this stuff really well. So, for instance, I just spent half an hour chasing down a bug that was basically just a stupid trig mistake. And so know the basic stuff really, really well. That's more important than knowing higher math, but only kind of knowing it. And so that means for some of you, if you're going into game programming, you may want to dust off a high school math textbook or an introduction to trig book or use some resources online. And the linear algebra courses that you'll be taking here are actually extremely relevant to what you're doing. So keep all that in mind. They're taught by math professors, so you may not immediately see the relevance to programming or computer graphics, but they are. And the better you learn this stuff, the better position you'll be in when it comes time to do this. Okay, so that's my motivational speech for today. Be good at math. And even if you're not interested in game programming and not going into that, still be good at math. And the most relevant course for you then is probably Comp 1805, which is really a math course. And most of you will be taking it next semester. And it's something a lot of students have problems with. But it is important. Okay. So where were we? Last class, we had just sort of hacked together this game where there's an ant that runs around trying to eat food. There's poison in the way, and I think we had got to the stage, so this game has 3 lives, whatever. I think we got to the stage where if we click on these poisons, they disappear. Okay. So I found about an hour and a half this morning to, although I wasted half an hour chasing down a trig problem, to upgrade this game, to add some features to it. And these upgrades are all basically polishing. So now we're at November 6th. So first thing is there's this sort of click to play screen, start screen available now, so the thing doesn't just start up and immediately go into play mode. And once you click, there's a soundtrack now. There's sound effects. When the ant eats something, there's I don't know if you can hear it. There's a little chip eating sound. And when the ant gets poisoned, there's a gagging sound. And difficulty actually increases. I didn't bring my pen today, so I won't be able to play terribly well. But notice that the ant's getting faster and faster. And something else that's happening is the amount of poison on the screen will be increasing if I can actually get up to 5,000 points. So every 1,000 points, the ant's speed picks up. Yeah. And then when the game ends, there's an extra sound effect, a scream. And then it goes back to the click to play thing. Okay? So this is a good chance for me to introduce a topic. It's really a shame that I forgot my pen this morning. It's really a good chance for me to introduce a topic which is finite state machines, which basically talk about, well, the finite state machines model a lot of things, but one of the things they model is stuff like what's happening in this game. And if we go and look at this code now, a lot of stuff has been refactored, but the important stuff is in the game class, there's now these 4 states: playing, dying, game over, and starting. So I'll just put these on the board. Playing. Well, let's do it another way. Starting. And these 4 states are representative of, our life in general. So life starts, and before you get going, you have to come out of the womb. So before then, you're starting. You press click to come out of the womb, and then for a while you're playing, and that's what you guys are doing now, right? You guys are young. You don't have full-time jobs, most of you, so you're playing around. Pretty soon you get to my stage where you're dying. And not long after that, it's game over. Okay? So these things are called states. Okay? And in computer theory, we make machines out of these things that are called either finite state machines or finite state automata. And one thing that we have that finite state automata have is what's called a start state, which you usually represent as one of these states having an arrow going into it out of nowhere. So when the game or program starts, that's the state that we're in. It's this start state. Okay? And then something happens, and we move from this start state into this playing state. And that thing that happens is a mouse click. Then we're playing this game for a while, and we move from the playing state into the dying state. So let's observe this in the game. So we're now in the start state. A mouse click happens. We're in the playing state. And the dying state, which we'll see in a second, maybe more than a second. The dying state is happening now. And now it's over. We're playing again. Okay? So when we eat poison, we move into this dying state, and then somehow this dying state finishes by itself and comes back into the playing state. And once we run out of lives, it's game over. Okay. So we were actually playing, we went into the dying state, and then we went into the game over state. So you may have heard it, there was the coughing, the choking noise. That was part of the dying state. This is, cough, choke. Then we transition from there into the game over state. Okay. And now, and that was what happens when lives equals 0. Okay? And from the game over state, we went, or we can go now, if we click, all the way back to, well, we don't actually, sorry, we didn't have to click to do that. It actually automatically went back into the starting state. Okay? So it's clear when this happens. Starting happens, from starting to playing is from mouse click. From playing to dying is what happens when you eat the poison. From dying to game over is what happens when your lives is 0. But then there's these two other arrows which seem to just happen apropos nothing. And actually, if we go in and inspect the code, these two things happen because there's a timer that we set that causes them to happen. And so here, this is the start timer, does this, and this is what's called a restart timer that causes this thing to happen. Okay. And so actually, as the game gets more advanced, you end up with this bigger and bigger state machine, and it's harder and harder to keep track of. In particular, it's harder to see this, understand this state machine just by looking at the code, because even if you have a reasonably good monitor, you can only see maybe 75 lines of code at a time. This game has now grown to 329 lines of code. So you don't see the whole state machine by inspecting the code. So it's actually helpful to draw these down on a piece of paper. And if you think about the games that you play, these sort of temporary states are fairly common. So for example, it's pretty common to have a cutscene of someone dying for a little while, which is totally different from playing the game, right? Your character dies, there's a time elapses while you watch them die or choke or do whatever. Same thing over when there's a game over kind of thing for a while, there's usually something special happens. In longer games, there's transition scenes between levels and so on. So you get these fairly big state machines, and it's worthwhile drawing them to understand what's happening. In fact, there are whole, it's not exactly programming languages, but there are whole ways of programming that revolve around creating these state machines with a computer program and then pressing click, and what happens is a code gets generated that makes this state machine. In fact, the entire, you may have heard of UML, the Unified Modeling Language, is basically creating these state machines and saying, make some code out of this machine rather than write it yourself. But don't worry about that. You'll learn about that later. And sometimes, you know, just for your own sake, it's helpful to annotate these figures a little bit. Like in the playing state, some special stuff happens. You know, the ant moves. That's one thing that happens. We also check for eating. So if the ant is currently eating their food, we also check for poisoned. And that's why we're actually able to know when it's time to move to this state when the ant gets poisoned. In the game over state, we draw the text game over on the screen. In the dying state, when we move into it, we play this coughing, choking sound, and we don't do anything else really. And in the start state, we actually draw the text, click to play. So starting next week, you'll be doing a more, well, you'll be making your own game or whatever you want to call it. And so, you know, a good way to start, well, maybe it's not always the best way to start, but something that you usually eventually find yourself having to do is making one of these diagrams and figuring out exactly what your code should be doing if it's not doing. Yeah, so there's the diagram. And we can look through the code a little bit to see if we are correctly implementing it. There's no guarantees, of course, but so for example, from the start state, we press click and we get to play. So let's see where we would find that code. That is in, well, now when the user, let's see, if we're in the start state and the user, we receive a mouse button down event, then we do a restart. And a restart actually puts us into, resets everything, number of lives and all that stuff, and puts us into the playing state. So if we look at restart, restart resets our lives, resets our score, and then starts. And start plays the soundtrack, sets the ant's position, creates new food, new poison, and puts the state into playing. From playing, eventually at some point we eat poison, and that sets our state into dying. There it is. So when we end up eating poison, we call self.die. Self.die reduces the number of lives, puts us in the dying state, plays the sound of an ant dying, and sets a timer. And the length of that timer is 1 second plus the length of time it takes to play that sound of the ant dying. And that timer sends us a start event, which takes us out of the dying state and back to the playing state. Okay. So it's nice to have these diagrams because there you get the whole thing in one picture. In the code, really this stuff is little bits of code that are spread out all over the place. And so this is the kind of thing that you should probably be doing when designing your own game, unless it's really, really simple. But even then, even the simplest games have usually some states. You know, there's usually a click to play state, a beginning splash screen, or waiting to play, and then usually the game ends, and it's not so nice if all that happens is the window closes as soon as you lose your last life. You usually want to do something nice. Okay. So, any questions about that? Yep. Yeah, sorry.
Like you use it as a check somewhere, or
For what?
just as the state?
Well, I mean, so when we die, we just set the state to game.dying, and there's places all over the code where we check the state. So, for example, when handling events, right? So when we get a refresh event, that's one of these things that happens 30 times a second, we always draw the screen, but it's only if we're in the playing state that we, for example, make the ant move, we check if it's eating, and we check if it's been poisoned. In the other states, we don't do that. So that's why the ant just sits there while it's dying, or it sits there when the game is over. In the quit, well, there's nothing special about quitting. But mouse button down gets treated two different ways depending on the state you're in. So if you're playing the game, we call this function called click, which is going to go and check to see if you clicked on poison. And if you're in the start state, well, then we call restart, just restart the game. So this state variable gets used all over the place. And another place where it gets used is in draw. So we always draw the food, we always draw the poison, we always draw the ant. We always draw the score and the number of lives up at the top. And depending on these, whether if we're in the game over state, we also draw game over. And if we're in the starting state, we draw click to play. So the state variable gets used throughout. So any questions about that? Good. Anybody done assignment 7 yet? Anybody started assignment 7 yet? Yeah. How is it? All right. Tricky? Easy? Yeah. So I think for some people it's going to be tricky even to do the first part. And then for others, it's just going to be the bulk of the work is taking what's basically just a little prototype and turning it into something more like a real game with all the features of a game. But start as soon as you can. And how many of you have been to tutorials? Okay. And how did that go? You get anywhere? So it's hard for me to know how far people can get in 1 hour. So what I did was I sat down for about 45 minutes and did what I could, and then that's the exercise I gave you for the tutorial. So how far did anybody get? The ball dropping and bouncing? Okay. Yep. So the rolling? Or just the moving around? And the space bar too. Okay, good. Yeah. So that's pretty good. I think probably not too many people got that far. So one thing for the tutorials from now on, essentially, So this one suggested that you could work in groups, but even talk to people who are not in your group. So don't get totally stuck trying to figure something out by yourself in the tutorials. It's better for you guys to talk to each other. If you're really good, then explaining things makes you even better. Makes you understand them better. And if you're having difficulty understanding, it's nice if somebody who really understands can explain it to you. Okay. All right. So that's where we're at now, and now it's kind of a semi-full featured game. The only thing that I'm really dissatisfied with is this movement of the ant. And in fact, the first prototype of this game that we made, the first thing they said was, well, can't we make the ant go in the right direction? So the ant's just sort of translating around. It's always pointing northeast for some reason. It's not terribly realistic. So the question is, well, can we make this movement a little bit more realistic by maybe pointing the ant in the direction that it needs to go? And the answer is yes, but it's going to take us some work. So I guess the first thing we should do is maybe figure out where that work should happen. So the ant is a game object, and game objects, they initialize themselves, they have an image and they have a position, they can draw themselves on a screen, and they can tell you their size. The ant can do a couple of other things. In addition to all those things, it can choose its food and it can move. Now, if I want the ant to appear differently on the screen when it's moving, so where should that code be? In the ant. And what should that code, where should that happen? What function should I write in the ant to make it appear differently? What's that?
Angle.
Well, we'll want to maybe include some functions for computing angles and so on, but what does the ant really need to do differently than other game objects? It needs to rotate, but there's something that all game objects do that the ant needs to do differently.
Has to find direction of which way the nearest root is.
Well, not all game objects do that stuff, but there's something all game objects do, and ants shouldn't do it the same way. So all game objects initialize themselves. Fine, we already initialize ants a little bit differently. They all draw themselves and they all know their size. So what does the ant need to do differently? It already does moving. What does it need to do differently than the game object? Yep. Yep, it already does that. Yep. Drawing. Okay. So the ant is going to be just a different kind of game object that doesn't have the default behavior of just drawing an image at a location. It has to draw an image that's been rotated or something so that it looks the right way. And so it's actually the ant's draw on, it's this draw on method that we want to be different for ants. So in the ant class, we'll override this draw on method. So that's the thing that takes this ant and draws it somewhere on the screen. Okay, so here is where things are going to become quite confusing. And again, I'll need a picture for this. So when we move the ant, So let's sort something else out first. When we move the ant, if you remember how we did it, we compute the ant's position, we compute the target's position, and then we compute a unit vector that points from where the ant is towards the target. And then we move the ant in that direction, the direction of that vector multiplied by the speed of the ant. Okay. So one thing that's maybe a little bit redundant here is this calculation of this vector, because when we pick our food, there's, the ant is here, the target is over here, and then we start moving the ant like one step at a time towards that thing, but the step that we take at each time is exactly the same. So the vector from the ant to the target stays the same, at least the unit vector. So calculating this unit vector is actually something we can do once, and we only need to do it when we pick a new food item for us. So when we pick a new food item, we set the target. Now we can calculate this vector, and we'll save it in something called, let's just call it UV. Now when we move, there's no need to recalculate it anymore. We can just say, reuse that vector. So let's make sure we didn't break anything. We broke something terribly. Bum, bum, bum. Oh, that's why. We overrode draw on and never, there we go. Okay. So that didn't break anything, right? Because the ant basically moves, once it's picked its target, it moves in a straight line towards that target. The direction of its movement never changes. So we'll calculate that and save it for our use later. So now we want the ant, the picture of the ant, to be rotated so that it's pointing in the direction of movement. And there's a bunch of things that really complicate this. So here's one aspect. So this vector UV, which gives us the direction of the ant. So it's a vector of length 1. And that means that if you think of the vector, as an arrow that's sitting on the origin, then it points to some point on the circle here, right? This is this vector UV, the unit vector that's the direction that the ant is traveling in. It has two components. It has a 0 coordinate, which we call the x coordinate, and a 1 coordinate, which we call the y coordinate. So those are the two components of u and v. Okay? That's great. So if we're going to do a rotation, then what we want to do is take this point and turn it into an angle somehow. Okay. So in particular, the angle that we can measure directly, basically, is this angle here. Call this theta. So that's the angle we want to know, because that will somehow determine which direction we want to rotate it to. Okay? Now, does anybody know, has anybody ever seen before, if you're given a point on the circle, given its x and y coordinates, which is what we have, how you can get this angle? There's sine, cosine, not quite, yeah. Yeah, so sine, cosine, and tangent are all things that are all functions that take as an argument an angle, and they can give you, for example, cosine gives you the x-coordinate from the angle, sine gives you the y-coordinate from the angle, tangent gives you the ratio of the y-coordinate over the x-coordinate. But we want to go the other way around. We're given these things, and what we want is this angle. And so if we go to the math library, and we have to look at this fairly carefully. The function that we want is a tan 2. Okay? So this takes two arguments, the x-coordinate and the y-coordinate. Interestingly, the y-coordinate comes first. And it gives us this angle here measured in radians. So remember, radians are always a number between 0 and, or usually a number between 0 and 2 pi, right? So 0 is over here pointing directly at the x-axis, and as we go around, this angle increases until it increases all the way up to 2 pi and then wraps back to 0. That's a good question. So isn't it the other way around? So you've studied trig before, and the picture you always see there is something like an angle that's measured this way. Why is that different for us?
Because the y is.
Yes, because in every other field, y-coordinates increase upwards. In computer graphics, y-coordinates increase downwards, which means that the whole picture is inverted, which actually means a lot of things. Well, it means that we measure this angle in this direction, so we've actually reversed the orientation. So this thing measures angles basically counterclockwise from the x-axis. This thing measures angles clockwise from the x-axis. And read carefully the documentation here. A tan 2, and this will probably become important later, doesn't give us a number between 0 and 2 pi. It actually gives us a number between minus pi and pi. So if we have a point up here, this will give us a negative angle. In fact, it'll give us this angle here, but negated. Okay? So all the way down to, this will go all the way from here to just shy of minus pi, and all the way over here, just shy of pi. So if we're rotating clockwise, we'll go up to pi, counterclockwise all the way up to minus pi. Okay. All right. So let's get that angle. So this is for drawing purposes. We'll say theta is equal to math.a tan 2, and we need the y-coordinate is the first argument, and the x-coordinate is the second argument. Okay, so now we have this angle theta. Now, what do we want to do with theta? Yeah.
You don't have self-value in a second.
Oh. And so what do we want to do with this angle theta? Yep. Okay. Pygame.transform.rotate. Pygame transform rotate. And it's important to read the documentation. So, well, we can try not reading it and see what happens, or reading it quickly. Okay, transform rotate takes a surface and an angle. Terrific. Let's use that. So we got our angle, and now we say image equals pygame.transform.rotate. The surface we want to rotate is the image of the ant, and the angle that we want is theta, right? Looks good. And then draw centered theta, or this image, onto the screen at the current position. See how that works. Ant object has no attribute UV. That's just a silly thing. Doesn't seem to do anything. Yep.
The angle is raised, so it has to be increased.
Yep. So here's back to the documentation. Pygame transform rotate, unfiltered counterclockwise rotation. The angle argument represents degrees and can be any floating point value. Negative angle amounts will rotate clockwise. Okay. So, all right. Now, if we don't think this through carefully, we can say, I know something about this stuff. In math, I skipped over degrees. Take an angle x in radians and convert it to degrees. Sounds like what we want. So we've computed theta in radians. Let's prefix it with an r so we don't forget it. To get it in degrees, we say math.degrees, theta in radians. Let's try that. Still not quite right. It's worse than that. So the rotations are happening, and they were happening before, but they were so small we couldn't see them. Hey, look, it works perfectly. Oh, no. Yeah. So to get this to work, we can just keep plugging away at the code like this, or we can think it through. Okay. So let's think it through. So this is a picture of the way we have things represented, directions and angles measured in radians. In our game, if I look at there's the image of my ant. So one of the first issues is the image, actually, when it's not rotated at all, has the ant pointing 45 degrees. Okay. So that means if we do a rotation of 0, then the ant's going to look like this. Okay. Whereas here, a rotation of an angle of 0 means that the ant should be pointing directly in that direction, right? So what we want first, or maybe as a last step, is to get the ant rotated this way. so that it's facing, facing this direction here. So in Pygame, transform, rotate, what will we do to our angle to make that happen? Add 45. Is that true? Do we add 45? Yeah. So Pygame transform rotate does a counterclockwise rotation. If we add 45 degrees to this, we'll rotate counterclockwise by 45 degrees. The end will be pointing straight up. So we actually have to subtract 45. So sort of the last thing we'll want to do is deal with the fact that, deal with that thing. So we want to subtract 45. Okay. So that takes care of that. Once we've done that, we can pretend that our ant image was good to begin with. And so if we rotate by 0, we'll get a picture of an ant facing this way, due east. All right. Now, in this picture, which is what we're working with our internal representation of coordinates. So what happens, let's say this is exactly the picture. We have this direction, this vector pointing this way. So the number that we have, theta here, is it positive or negative? It's positive. So if on this half, all the thetas are positive, on the upper half, all the thetas are negative. Now, if this is our picture, and this is what we have here, do we want to rotate the ant a positive or a negative amount? So we want to rotate this much. Is that positive or negative? Negative. Okay. So that tells us that actually this angle that we have, we want to negate it. Okay? So when this angle becomes, when this angle is positive, we actually want to subtract it from the rotation. When this angle is negative, so that's counterclockwise, we want to add it to the rotation, which means in either case we want to change its sign from negative to positive. So let's check that. So there. Now we got it sorted out without too much hacking around. I mean, we made a couple of trials to see if we could just do it in our head, but it turns out it takes a little bit more thinking about it than that. So that looks a little bit better. So there's still a couple of unrealistic things about this that I'm not too happy with. One is that the ant's legs aren't moving. For that, we'll have to do a bit of image editing and make several different pictures of the ant that we cycle through. I didn't have time to do that before class. But another is, I don't like this, this instantaneous turning. So the ant just, it can turn 180 degrees in one step. It just kind of jumps around. And so what if we tried to make that a little bit smoother and actually make it actually turn like a real ant? Or if any of you are going to do anything that remotely resembles a game with a car, that turning is somehow tied to moving at the same time. So turns aren't instantaneous, right? It would be nice if they were, if you could parallel park by just driving up beside your spot and driving in sideways, flipping in. But we can't do that. So if you want to do some kind of realistic turning, that means these rotations that we do here, they should maybe actually take place over a series of frames, not just a single frame. Okay. So let's think about how we could do that. All right. So I've already said that choosing, well, first of all, does anybody have any questions about what we've done so far? Yeah. Why we used arctan? Because arctan is the one thing that takes both an x-coordinate and y-coordinate and gives you back an angle. So the tangent is a function of the x-coordinate and y-coordinate. So the inverse tangent gives you back the x-coordinate and y-coordinate. And you usually want to look, in most languages, there's this math library, atan2, the one that takes both things as an argument. Okay. There's usually a function called atan that takes one argument, which would be the y-coordinate divided by the x-coordinate. But there's actually not enough information there to distinguish between things which are, for example, pointing 45 degrees, let's say northeast versus southwest, because the signs of the x and y coordinates cancel out. So atan2 is the thing that takes an x and y coordinate of a point on the unit circle and gives you the direction, the angle to that point. Okay. All right. Okay, so let's try and make this a little cleaner and a little bit nicer rotation happening over a period of time. So maybe the first thing we should think about is this vector uv here. Maybe this isn't the best way to represent the direction of an ant, right? This uv is always, or almost always, a unit vector, except for that first instant at the beginning. But now we can say that it's always a unit vector. So it's a vector that points from the origin to some point on the unit circle. Is there maybe another way we could represent it? Yeah?
As an angle?
Yeah. So just as an angle would be enough. So rather than represent this vector directly, let's just represent it as an angle. And let's do that in radians, like this left side of the picture here. Degrees are for, degrees are for computer graphics people. We like radians. So rather than represent UV directly, we'll just represent the direction, which means that after we choose our food, we don't store UV, we store the angle UV, which we get from math.atan2, UV at 1, UV at 0. Now, when we move, we want to move in this direction that we have now, which is given by an angle. So we have this thing here, it's called the direction, and we want to know the x and y coordinates. So what are the x and y coordinates from the direction? How do I get those? Sine and cosine. Cos and sine. So the cosine of that angle gives me the x-coordinate. And the sine of that angle gives me the y-coordinate. Okay, and now when we draw, well, we don't need to compute this thing anymore. We've got it already. It's just called self.direction. But we do need to convert it to degrees. We do need to negate it, and we do need to subtract 45. So let's see if we broke anything. Seems okay. So didn't affect the functionality at all, but we have a slightly different representation for our direction now. It's just the angle measured from the x-axis in radians. Okay. So now what we want to do is have the ant, when it picks its food, not just flip directions like this, but rather have that happen over a period of time. So that should happen during the moving. So we'll take this out of choose food, and we'll split this move thing into two parts. Here we want to move a little closer to the food. Here we want to turn towards the food. So we go back again to computing this angle UV at every, not this angle, but this vector UV at every frame. And we also compute now this angle theta, which is the direction that we would move in if we wanted to go directly towards the food. So we're moving in self.direction, in this direction, and we want to turn that so that it's a little bit closer to the food. Okay. So here's where things can get very confusing, and it's what I spent half an hour doing before class, is ironing out this issue. Okay. So we've got our own direction that this ant is facing. So and that thing is given by this angle here, and this is given by self.direction. And we have another direction, which is the way the ant should be moving. The direction the ant should be going to get to the food, so it has to turn a little bit in that direction. So that thing is what we have now called, let's make it easy for now. We've now called that thing, so the food is over here. This thing here is called theta. That's the thing that we've just computed. Now, okay, everything's clear so far? We have this direction the ant's going in, it's measured by this angle. We have this direction theta that the ant should be going in, it's given by this thing. And we like to turn the ant into this thing. And we'll start by just turning it in one step, but eventually we'll just want to turn it by a few degrees during each frame. So what's the difference between those two angles? It's not not a difficult question. What's the difference between x and y? What's the difference between a and b? Minus. It's subtraction. So we're looking at theta minus self-dot direction. So that's going to be our turn. And in this picture, that thing, so if I take theta and I subtract self-dot direction, I get something which represents this angle here, the difference between the two. And in this case, self-dot direction is bigger than theta, so this thing is actually negative, which means in this picture it represents a counterclockwise turn. Okay. So we can go turn is equal to theta minus self-dot direction. And now, if we just want to do a one-step turn, it's easy. We just say self-dot direction plus equals turn. Right? And then ultimately, what's self-dot direction after doing all of this? Well, it's theta minus self-dot direction plus self-dot direction, which means it's just theta. So let's see if that works. Good. We didn't break it yet. And for these things, it's sometimes good to let it play out for a little while, because it's very easy to introduce mistakes that only happen, for example, when the ant is turning from somewhere going downwards to somewhere going upwards, or when it's turning from sort of northwest to southeast. It starts to become easy to make these kind of mistakes. Okay? So, all right. So this basically, computes the difference between the ant's direction, the food's direction, and then adjusts the ant's direction for that. Now what we want is, we want the ant to do this, but we don't want it to happen instantly. So we want the ant maybe to only be able to turn, I don't know, some ratio of pi. So let's say math.pi over 10. So even if the turn should be really big to go in that direction, we won't let the ant turn more than a little bit. Math.pi over 10, let's say. And all right. We also have to worry about the turn being negative, so we won't let it turn less than minus math.pi over 10. And then we'll adjust the direction that way, and we better tie this to the speed. So let's see what that does. Self.speed. Not quite right, eh? So again, this is the kind of thing that you want to just sort of hack your way through without thinking too hard about it, but actually it's not that easy. Yeah. So, doesn't seem to be working for us. So back to this picture on the board. A couple of things going on here. Theta is something that's given to us by a tan 2. And so that means it's between minus pi and plus pi. So maybe to make life easier for us, we should also do the same thing with the ant's direction, so that we're talking about apples and apples instead of apples and oranges. So let's take the ant's direction. So if the ant's direction, which should be between 0 and 2 pi, we actually want it to go the other way. So if it's bigger than math.pi, then we want it to be a negative number, and we want it to make up the difference. So it should actually be equals, okay. Make sure we didn't screw anything up there. No worse than before. Whoa. Yeah, that's pretty cool. That's really impressive. Okay, so still doesn't deal with it, but now we can still at least check out what's happening. Percentage 0.2 f pi. So we want to know our direction. We want to know theta. So our direction has gone crazy, which is what's causing this thing to blow up. So if self-direction is bigger than math.pi, self-direction equals self-direction minus 2 times math.pi. And here we're doing this turning is equal to theta minus self.direction. That's probably not, so that's somehow getting too big, right? So this could, if this turn is positive and it's wrong, then it could keep blowing up. Let's, oh, I see. So we're back to something that at least works, isn't so screwed up. But we want to do this turn slowly again. So kind of works. So it's a little bit like Zoolander. It can only, well, it's not true that it can only do left turns. It can do both left and right turns, but somehow it decides in a strange way whether to turn left or turn right. The good news is you can get going in any direction by turning only left or turning only right, as Derek Zoolander knows. But it's kind of frustrating for the game player and a little bit weird looking for the game. So how would we fix that? So in particular, if we look at these turns that we've been doing, yep.
Do you have a plan to work the smaller
Yeah. So we have this, we've computed this turn here, which may be positive or negative. Now, what's the largest angle we should ever have to turn? 180, which is called what? So if the turn is bigger than math.pi, then something fishy is going on. And similarly, if the turn is less than minus math.pi, something fishy is going on. So what should we do if the turn's bigger than math.pi? Turn the other way somehow, right? So how do we do that? Yeah, so if the turn is bigger than math.pi, then if we take math.pi, 2 times math.pi, and we subtract the turn, then that's still not right. Why is that? So if the turn's bigger than math.pi, which means the ant's trying to do something like we're trying to turn into a direction like this. So we'd be trying to go clockwise more than 180 degrees. And now what's math.pi minus turn? What does that measure? Or 2 times math.pi minus turn? So this is turn. 2 math.pi minus turn is what's left, right? So that's this section here. So that looks like what we want. But it matters to us whether this is positive or negative, right? And what do we want it to be? We want it to be, right, so this one is what? Let's think about it a little more carefully. In fact, let's drop this, this view of things and look at it this way. See how we got turn. We took 2 numbers that were between minus pi and pi. Those numbers were the direction of the ant and theta. And we took theta minus direction. So theta minus direction is this length here. And it could be either positive or negative. In this case, theta is bigger, so theta minus direction is positive. And so in that case, we're worried that it's bigger than math.pi. And if it is, what should it be? So theta is bigger than math.pi. So that means it's a positive number. We want it to be a negative number, and we want it to be the right negative number. So in this picture, that means we want it to be this length, the negative of this length, right? Right? Don't ask me, I was just confused by this for about half an hour before class. So if the turn is bigger than math.pi, we want it to be the negative math.pi 2pi plus term. Right? This is positive. 2 times math.pi minus this thing gives us this thing here, but we want all of that negated. So we actually want minus 2 math.pi minus this thing. All right. And otherwise, if the turn is smaller than math.pi, that means our picture looks like this. Minus pi. We have this would be our direction. Theta. What we have is this number, which is negative, and instead we want it to be positive. We want the positive version of this number, which we should be able to get just by taking 2 times math.pi minus term. All right. And now we cross our fingers. Oh, we screwed it up. So we're off in one of our tests. Anyway, we'll fix that up. Well, I'll fix it up on the code online.